Hi everyone, this is Raphael. Today's Learn and Share is lightweight authentication of web data via Gavel and proof. We have Shang-Xie from Bado Labs who is going to present it. This is a very interesting work which follows up a bit on DECO and TLS Notary using malicious 2PC to prove TLS connection. Very excited about this talk, and I hope you are. So thanks a lot to Shang-Xie for being here, and we are all ears.
Yeah. Thank you for the introduction. And yeah, let me share the screen. One moment. Yeah, cool. So yeah, it's very happy to be here to give you a presentation about our work. And yeah, I think it is kind of free for anyone to interrupt me for any questions during my presentation, and I'm happy to answer their question. So yeah, the work of this presentation is about how to authenticating web data with interactive anonymity proofs, and yeah, it's a joint work with Kang, Xiao, and Yu. So yeah, let's start. So first, let's introduce the motivation on the background. So the problem is as follows. So there is a prover or client who has some information from stored in the server, and there is a way for the prover to query and get their server. So for example, you have a password, and you have an API key, and then you can access to a server and get your private information. The problem here is that how can the prover or the client to prove to a third party, which we call a verifier, that the information is actually from the server and it's not just some random data or just made by the prover by himself. And the key point here is that we cannot modify the server side because it's kind of impossible in real life that you need to change the server and then for these very special applications. And more importantly, what we want to do is that we want to prove any kind of this data for any kind of server. So yeah, it's kind of impossible for anyone to change the server side. And this is also the most difficult part in the product design. And a very concrete example is that I want to prove to a third party that I have enough ease in Coinbase. How can I do that without any changes of the Coinbase server? So that's a problem here. And so to make the problem, also solution more general, so we are considering the TLS protocol. So which means that the prover using TLS to access the server. And this is kind of very common, and the TLS is a Web2 standard and is widely deployed in a lot of applications. For example, when you're using browsers, you're using HTTPS, and then you're using TLS. So yeah, we are focusing on TLS. So there is TLS 1.2 and TLS 1.3, and in this presentation we are now focused on 1.2. But the technique here is kind of very straightforward to extend to TLS 1.3. So yes, so I think so far so good. So let's go into a little bit details of the TLS protocol itself. So there is two phases of TLS. So one is called a handshake phase, and the other one is a record. So handshake means that the client and the server to run a key exchange protocol and to get a shared secret key and for the record phase. So they are using very standard or classic Diffie-Hellman key exchange. So the protocol is very simple in general, and the client send some kind of random values to the server, and the server send back to random value x times g, which is elliptic curve point and the certificate and the signature, and then the client send back to a yg to the server, and the shared secret is xyg, which is very standard Diffie-Hellman key exchange, and using this shared key material, the two parties can derive session keys we call KC or KS for the record phase. So in the record phase, the client server using these two keys, symmetric keys, to send and receive messages from each side. So here, all the encryption is using symmetric keys like AES, DCM, or CHA or something like that. So it's quite efficient in this phase. So that's basically the framework of TLS. And the framework is kind of simple, but I have to say the details are quite complicated. And that's why we spend a lot of time to implement all the details. So yes, having this background of TLS, so I think there is a first trial that how to solve the problem I mentioned before. So there is kind of very simple way. Kind of very simple way. So in this way, after all the TLS protocol, after handshake, after the record, in the record phase, the prover send the request with the secret to the server, and then get back to the message, and everything after this kind of TLS session, the prover can get all the transcripts during the internet. And a very simple way to do that is that the prover can just use snarks to prove that, okay, I know all the randomness, all the secret, the message that generated these transcripts, and send the proof and all the transcripts to the verifier. Of course, the verifier can check the proof. If the proof pass, then the verifier says, okay, yes, I believe you. So this is a very simple and a very natural way to think about the problem. So yeah, it's kind of very simple in general, but unfortunately, this solution does not work. So there is a very simple attack. So yeah, the prover use random do the TLS protocol normally. Everything is correct and is valid, but when the prover generates the proof, so he replaced the value M, the valid ciphertext M, with another ciphertext of M prime. And the prover can do that because the prover get everything of all the symmetric in all the record parts, because get all the secret key to encrypt everything. So after replacing the ciphertext of M prime with M, then the prover can generate a valid proof and then send back to the verifier, and the verifier just check everything and everything will pass. But this is absolutely not what we want, because the prover can encrypt everything of M prime to the ciphertext. And the key point here is that the prover knows the secret key of the encryption, and he can generate any valid ciphertext of any data, and then go to the snarks and then generate the proof. So this is a key point, and this is the main problem that the natural solution I mentioned before does not work. Any question here? Maybe, yeah. If I'm not sure I'm clear enough. So if there's no any questions, I will go for the next slide.
I don't see any questions in the chat, no. So it seems
sure. Cool. Okay. So how to solve this problem? So okay, now that's the DACO protocol. So DACO protocol give a very nice a solution of the previous problem. So the key part is as follows. So instead of the prover as a client to run the TLS session with the server, so the verifier and the prover has to run a two-party computation protocol to connect with the server in the handshake part. And at the end of the two-piece protocol, the prover and the verifier will have the share of the session key, which is KP and KV. And the server, yes, there's nothing changed of the server. The server has the session key K, and KP and KV are shares of K. So yes, this means that the prover himself cannot control the TLS session or the TLS channel by himself, because he only knows partial of the key, or only knows the share of the key. And in the query part, so the verifier and the prover has to get help from the verifier to run a two-piece protocol to generate the ciphertext with the secret key and then send to the server. So yeah, here C1 is, it looks like a very normal ciphertext. Instead of that, the ciphertext is generated by the two-piece protocol. And then the server will send back to a response in the ciphertext C2. So the key part here is that now, the prover now forward the ciphertext to the verifier as a commitment of ciphertext, which means that after this step, the prover cannot change the ciphertext anyway. So as I mentioned before in the previous solution, the prover can change the ciphertext because he knows the secret key and there's no commitment of the ciphertext, so he can change anything he wants. So in this step, since the prover cannot control the encryption and decryption of ciphertext, and the prover send forward the ciphertext C2 to the verifier as a commitment, then the prover has no way to change the C2. So this can kind of avoid the attack before. And after that, the verifier will send back the share KV to the prover, and the prover get everything. So now everything's okay because the prover can decrypt all the transcripts, so he can see all the information he wants. And this time, the prover has the key, he cannot change C2 anymore because the verifier already get that. There's no way to modify it. And at the end of this procedure, the prover then run a SNOC to prove that, okay, I know KP secret message that generates C1, C2. So it means that, okay, the C2 is not kind of random ciphertext, is actually generated by or generated in the TLS session. Okay, and in generally, I think the DECO protocol here now give a very nice solution by using 2PC and a little bit kind of tricky to commit the ciphertext. And yeah, this kind of protocol will work for the whole solution, for the whole problem. But there is kind of drawbacks of DECO. The drawbacks of DECO is kind of, is about the efficiency performance. So in the DECO paper, they are using maliciously secure 2PC protocol. It's kind of very generic 2PC protocol. So they are using authenticated garbage circuit, which is kind of complicated. And it involves very large computation cost, and the memory is very large. And if you are familiar with garbage circuit, then AGC authenticated garbage circuit is kind of like 10 times slower than semi-honest counterparts. And another part is that if you're using SNOC, you have to prove some ZK unfriendly ciphers and operations. For example, they are working on CPC MAC cipher suite. So you have to prove SHA, or you have to prove AES, or even you have to prove multiplications over this binary field, which is kind of not that efficient, and the memory cost is very large. So that's kind of the performance issues in the DECO paper. So what the contribution of our paper is that we are using a new paradigm, what we call gobble then proof, to replace all these heavy part, these lightweight building blocks. So generally speaking, we can replace AGC with semi-honest garbage circuit. And then we can replace sticky SNOCs with interactive technology proofs. All these building blocks is very lightweight, but I have to say it's not a simple replacement. The details quite complicated. I just want to give you a a brief framework of what we are doing and to make it very fast. So especially the key point that when we are using IZK or interactive technology proofs, the current state-of-the-art IZK protocol is quite efficient. It's even efficient than the semi-honest garbage circuit. So in our whole protocol, the main bottleneck of the performance is actually the semi-honest garbage circuit. There is no kind of, the IZK part is very cheap. You can just ignore it in terms of performance. So yes, so let's go to a little bit details of all the ideas how we solve it. So the idea here, the key observation here is that when we are considering 2PC protocol, the case in this problem is not a general 2PC protocol. So the key point that at the end of the protocol, the verifier will send back the key shares to the prover. So we abstract the problem a little bit. So for example, if a prover and a verifier who wants to run a 2PC protocol on a function f, and the input of prover is xp and input of the verifier is sv, then they run the 2PC protocol and get the output y or yv and yp. And then at the end of the protocol, the verifier will send back xv to xp. So at the end of the protocol, prover will get everything of the secret part. So that's exactly what we are talking about in the previous DECO paper, right? So in this case, we kind of use more efficient building blocks to design this 2PC protocol. So there's the key point here is that when we compute when we compute this two-party computation, we're using garbage circuit. So garbage circuit is very suitable for this Boolean circuit, and there is a very nice property which is that the garbage circuit is actually secure against the malicious evaluator, which means that we only need to consider the malicious prover case. And in our protocol, so before the verifier revealing XV, we want the prover to commit XP and YP. So before I reveal everything, so the prover cannot change his input and output. And at the end of the prover, or at the end of the 2PC protocol, so the prover has to additionally prove that the output and the input are consistent with regard to the commitment value. So in this case, even the prover, the malicious prover, can introduce some kind of a malicious behavior in the 2PC protocol. At the end of the protocol, the verifier will detect that the prover cheat or not. This is what we want. We do not avoid the malicious prover. We just want to detect the malicious behavior of the prover. So in these cases, we are using the special case of garbage circuit, and we are using a very special IZK approved systems to prove the consistency with regard to the committed value. So this will enable us to use just a semi-honest garbage circuit. We don't need to use augmenting the garbage circuit to prevent malicious behaviors. So we just need the semi-honest garbage circuit, which is like 10 times faster. And then we use IZK to prove, which is like maybe 100 times faster than than Snarks or even other proof systems. So I think this is the main idea that we can make them much more efficient. So in the next slides, I'm going to describe a little bit about each step of the protocol and give a brief introduction of garbage circuit and the VOLE based IZK. Yeah. So in the handshake, it's actually a two-party handshake. So as I said before, the prover and the verifier will run two-piece protocol to share the session key. So in this case, yeah, I think the Deco paper called it a 3PC handshake protocol, which is kind of in this way. So after the server sent back to XG to the prover will forward everything to the verifier, and the verifier will check everything, and the verifier will generate a YG or YVG, and the prover will generate a YPG, and the verifier can set the EC point, the elliptic curve point, to the prover, and the prover add these 2 points and send back to the server. So which means that the DH tuple is not generated by the prover itself, it's generated by the verifier and the prover. So this case, he can do this to a 3PC handshake protocol. And the point here is that the verifier and the prover each get each party get like a secret value, and the task is that they want to compute this session key, the DDH tuple, and all of these stuffs are represented in elliptic curves. So the key point is that the verifier get point Z1, and the prover get a point Z2, and they want to compute the x coordinate of Z1 plus A2 in the elliptic curve. So if you do some math, so it's just to compute this Z equals eta square minus x1 minus x2, and eta means that this equation. And there is a very standard way to do this kind of a two-piece protocol, but it involves a few building blocks. So in the Deco paper, they're using fully secure M2A. M2A means that multiplicative to additive protocol, which means in the M2A protocol, so each one has an input and has output. And after the protocol, the addition of the protocol equals to the multiplication of the input, which can transfer multiplicative share into additive share. And this is all what we need in this two-PC protocol. So in the also it's always called the OLE protocol. These two things are the same. So in the Deco paper, they are using pair homomorphic equation and generality proofs to construct this M2A protocol. And we found that in our case, so we can just use a very weak OLE version. What we call is OLE with errors. So OLE with errors means that in the protocol, we can guarantee the privacy of all the input, but we cannot guarantee the correctness of the output. The building block alone is kind of very lightweight, and we found that using this weak building block still is sufficient for our protocol, which means the reason is that recall that at the end of the protocol, the prover has to prove that everything is done correctly. So even if in the OLE with errors protocols, the prover introduce some errors to the output, he can be detected by the verifier in the IDK proof. So the IDK proof can make sure that the prover cannot introduce any errors in this kind of situation. So we then can use OLE with errors with this kind of lightweight building blocks, and it's kind of maybe I think it's like 3 times faster or even more than using very general M2A protocol. So that's how we to improve the the two-PC handshake parts. And yes, the other part is that when we get a secret share or get a shared scheme material, we have to use a KDF, key derivation function, to derive different key materials for KS, KCKS. Yeah, the KDF function is kind of very complicated. It involves a lot of HMAC, SHA functions, and we actually implement or optimize all the circuits. So our optimization is that we found that some of the part yeah, here F means the compression function of the SHA function, of the SHA-256 hash function. So in the circuit, there is a lot of reused values. And we found that we can open some intermediate values to compute it in plane to reduce the AND gates of all the circuits. So we also prove that this way is also secure when we see FH as a random oracle. And in this case, we can reduce the AND gates by like 3 times. So which in turn improve the whole communication sites by 3 times. So yeah, that's the main idea that how we optimize all the circuits. Yeah, it's very complicated task, but we found a very nice way to optimize it and make it very make the number of AND gates much more smaller. So this is why this is one part of what we do in the KDF function. And then the other part is that when we focus on the record function, a record phase, we're now focusing on AES GCM. Yeah, here is a very simple description of the AES GCM. So given a message M1 to MN, so you are using AES and the key to encrypt or the counter, and then XOR the message, you get a ciphertext. In addition, you have to compute the tag, which is what we call ghash function. So I think we do not need to go into details of how the details in the tag functions. What we want to say is that in this case, the important thing is how we compute the edge part or the power of the edge part, because it's very natural to use the garbage circuit to compute AES. For example, AES only has like 6,000 AND gates, and it's very general. It's a very general way to compute the AES function. And the key point that part is that we how to compute the polynomial function of H, and H is also AES ciphertext. And there is a very general way to do that, is that you are using garbage circuit to compute everything, but it's quite heavy because the multiplication in the binary field is kind of very heavy, because one multiplication involves like 8,000 AND gate. So it's even heavier than the AES gate. So in order to reduce the overhead here, we now propose a new idea to compute the power of edge. So the problem now is, given share of edge, which means each party hold H1 and H2 respectively, and we want to compute the additive shares of the power of H. So the idea is very simple. So we are using A to M, which means the additive to a multiplicative protocol with arrows. With arrows means that we can guarantee the privacy, but we do not guarantee the correctness. So in this way, we can compute H bar 1 and H bar 2, and such that H1 XOR H2 equals the multiplication of H bar 1 and H bar 2. So in this case, the two parties can locally compute the power of H bar. And it's also the multiplicative shares of the power of H. And then we use OLE or use M2A with arrows to compute the additive share of the power of H. So in this way, we can make about 1,000 times faster than directly using GC. And all these A to M with arrows and OLE with arrows are very lightweight, just involves like a few OTs, and OT is quite lightweight in terms of performance. So that's basically the whole protocol, or the main framework of our protocol, and the garbage proof paradigm, and all the optimizations of handshake rate card. And the result is that we can improve the decode paper a lot. So for example, in the key KDF function, we can improve like 3 times faster. And the computation in terms of computation time, we are like about 10 times faster than DACO part, the DACO. And one thing we want to mention is that we actually did not implement the SNOC part of DACO. We only compare the MPC part. Even in this case, we are like 10 times faster than DACO. And we think that if you add the SNOC part in DACO, the improvement will be much more larger. And also we improve the communication size by 14 times, especially when the memory size is kind of 25 times smaller because we do not need to use SNOCs, and the Gabor circuit and IZK are memory efficient. So all these improvements allows our protocol to be deployed using browser extensions. So it's quite lightweight, and even the browser extension can run our protocol. And we actually integrate this protocol into our product. So yes, so far that's the main ideas and the main improvement of our protocol. And yeah, maybe any questions. And in the next slide, I'm gonna go into the details, maybe descriptions of Gabor circuits and the IZK stuff.
I do not see any questions in the chat. I do have a question, however. When you talk about 3 times, 10 times improvements in speed, you say that you were only looking at the MPC part, sorry, the communication part with DACO, if I understand well.
So yeah, actually we implement all the details of our protocol.
Yeah.
And we implemented the MPC part of DACO.
Yeah.
But we do not implement the SNOC part of DACO because it's kind of very complicated. And then we compare our whole protocol with the MPC part of DACO, and then we still have like 10 times faster.
Yeah. So I just wanted to confirm that these numbers take into account the proving time of your protocol, but not the one of DACO. Thanks a lot.
Yes. Yes.
Great. Thanks a lot.
Okay. So yeah, I think I'm gonna talk about a little bit about a Gabor circuit. Maybe someone is not familiar with that. So yeah, just a very brief introduction of Gabor circuit, which is kind of very popular in the MPC area. So Gabor circuit means that the scenario is that there is a Gabor and the evaluator. They know a function and they want to compute a function f and get the input fxy. So okay, so Gabor circuit is very familiar. It's very suitable for the Boolean circuits. So we're now considering Boolean circuits, means that all the inputs, all the wires are bits. Okay, so the function is public. So then the Gabor get the function and he get everything of the the layout of the circuits. So he choose random labels, 2 random labels for each wires of the circuits. So like A to G. So to represent 0 and 1 for use a random label. So then for each gate, the Gabor generate a Gabor gate. So for example, for the first AND gate, so using a double key encryption, symmetric encryption or AES, to use the input label as 2 keys to encrypt output label. And the way he encrypt is according to the gate. For example, if you use the AND gate, so the order is like 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. So the encryption is like you have 4 ciphertexts, then you have 4 ciphertexts for each gate, and so then the Gabor can generate all the Gabor gates for all the gates, and then and then the Gabor can send all the Gabor gates, which is Gabor circuit, to the evaluate. In addition, the Gabor will send the input label according to his input. For example, here is like A0 and a C1, and this is very secure because A0 and a C1 is just random labels. Does not the evaluate does not know any connections with the input, and also the Gabor will send the output label, the output label of the circuit G001, and it tells the evaluate that G0 means represent 0 and G1 represent 1. So in this case, the evaluate and the governor also run oblivious transfer, means that the evaluate take his input to the oblivious transfer, and the governor also send the labels to the oblivious transfer, and the evaluate will get will choose the label according to his input B1 D1, and the governor does not know anything about the result, and the evaluate does not know anything about the other part. So in this case, the evaluate can get all these input labels, and he can do the decryption, means that he can test all these 4 ciphertexts and decrypt use the encrypt label to decrypt the output label, and then he can actually compute to G1 or G2. For example, in this case, he will get G1, so the output is 1. So it's basically the main idea that proposed by Yao, like back to 86, and I think there's like a lot of work in this area, like 40 years after GC is quite efficient. So one thing I want to mention is that the security guarantee of GC is highly asymmetric, means that, as I said before, in this case, this GC protocol is secure against the malicious evaluator. And this is a very nice property, especially in our protocol. And yes, but it's only secure against the semi-honest garbblers, because the garbler can, gobble a different function f prime to get information of the evaluator. So if you want to design a malicious secure garbler circuit, for example, like authenticated garbler circuit AGC, so all you have to do is to avoid or find a way for the malicious to avoid the malicious garbler to gobble a different function f prime, what we call it selective attack. So yeah, this is kind of the security property of GC. And after 40 years, GC is quite efficient. So for example, like half gates or 3 halves, so it's state of the art GC protocol. So in our protocol, we are using half gates. And if you want to use 3 halves, you can cut the communication size by like 25%. But the computation overhead is a little bit higher by half gate. So in our protocol, we are now using half gates. And the current implementation of GC, like EMP toolkit, can now govern like 20 million AND gates per second, and XOR gate for free. So yeah, in our C++ version, we are using EMP toolkit to implement, the garbler circuit, and it's quite efficient because we can use ASNI instructions to make it extremely fast. So in the garbler circuit, the bottleneck of GC is not the computation size, is the communication size. So in our, for example, in half gate, if you want to gobble one AND gate, you have to send like 256 bits. So the overhead, so all the communication, all the bottleneck of the communication comes from the garbler circuits. Yeah, so far is the garbler circuit. So yeah, I'm gonna tell you a little bit about the IZK part. So why IZK is very efficient, and why IZK is much more efficient than SNARK, but it also has some IZK also has some drawbacks, because, for example, it's only private coin, it's not a public coin, so we cannot make it non-interactive. But in our case, this is sufficient because we already use 2 PCs already interactive. So IZK is it's perfect in our case, and we can make it very fast to prove Boolean circuits, especially in our case, all the stuff they want to prove is the Boolean circuits. So what I want to introduce is this, what we call VOLE based vector oblivious linear evaluator based IZK stuffs. So before I introduce the VOLE based IZK, I assume that there is oracle can generate this what we call VOLE tuples, or it's just the COT tuples. So in this case, the verifier will have a global secret delta, and the VOLE procedure will generate massive tuples of a random what we call ATMAC, information theoretic MAC. It's about the verifier has a key KI, and the prover will have a MAC MI for a random bit BI, and all these numbers satisfy this linear equation. So it's KI equals MI times BI plus BI times delta. Here, K and M are string bits, so like it's 128 bits, and the BI is a random bit. So in VOLE based IJ case, we have to implement VOLE can generate as many tuples as we want, and we found that there is a very efficient way to generate this kind of tuples. It's kind of for free in some sense. So given this kind of VOLE tuples, we can construct IJK protocols very efficiently. And one thing I want to mention that this ATMAC is actually you can see it as a commitment of the BI. So yeah, when each party open the value, there's no way that you can say something different. So it's actually interactive commitment schemes, and this is also very important in our gobble them proof paradigm, because we don't need to design or implement a hash-based commitment for all the input and output. We just use IJK and just use VOLE tuples to make it a commitment and make it for free. This is why we can make it very efficient. So in this case, so the prover, once we get this kind of tuple, when the prover has some witness, which is called a W or W1 to WM, which are all bits. So we have a very efficient way to commit or to make an ITMAC of this specific input WI. The prover just using WI minus BI and send the result to the verifier. This is safe because BI is random, so the verifier cannot get any information on WI. And then at the end of the protocol, verifier and the prover can get ITMAC of WI, which is a commitment of WI. And also this kind of linear relation is homomorphic. It's additive homomorphic. So if it's a XOR gate, you can just locally XOR all these numbers. So the difficult part is that you have to prove multiplicate. So here the multiplication is AND gate. So when we are considering Boolean circuits. So in this case, the prover and the verifier have three ATMACs. So the verifier then compute like K1 minus K1 times K1 K2 minus K3 times delta. So in this case, you can do a kind of a math. Then you find that there is still a linear equation as long as B3 equals B1 times B2, because if this is the case, the last term, the quadratic term will vanish, and this will make it a linear relation again, which is very nice in our protocol. So if this is AND gate and is true, then the verifier and the prover can get another linear equation of all these blue part and the yellow part. And at the end, the prover can first mask the previous part, because there is some kind of information may leak some information of the equation. So just the invoked VOLE part to get a random fresh tuple and mask the previous part and open it. Then the verifier can check with this very linear, very simple linear equation. And then when you're considering, multiple gates, so you just use a random linear combination to make it very simple. So in this way, we can prove AND gate very efficient. Especially we can prove the gate, prove the circuit gate by gate, which means that the whole protocol is memory efficient. So you don't need to load all the circuit into memory. You just to prove the circuit gate by gate. So it's memory efficient. And some numbers here is that IZK is basically fast. For example, the Quicksilver paper, we can just using like less than $2 to prove 1 trillion AND gates, and about 2.5 USD to prove 1 trillion multiple gates over Marsden prime field, which is much larger than the it's not just the AND gate, it's a multiplication gate over a large field, and the configuration of the machine is very normal. Also, we have other applications of IZK. For example, if the circuit is repeated, for example, in AES-GCM, there is a lot of AES circuits which are the same with different input. So in this case, we can even reduce the communication size of the protocol. But the computation overhead is kind of a little bit heavier. So in our protocol, we do not use NML right now, because when we integrate to browsers, the computation power is very limited, so we cannot afford this NML protocol in that case. And also we also design ZKML protocols using IZK. So we can prove ResNet 101 inference. I think is the complicated model so far we can prove, as far as I know. Yeah, but one important thing that the whole protocol is interactive. It's not publicly verifiable. But yeah, we can show that IZK is powerful enough to prove very complicated applications. Yeah, so that's IZK, and yeah, put everything together. So in our case, so we first use a semi-honest GC and to handshake, and then we use a semi-honest GC to encrypt the query part, and after the verified get sent back to the prover, we're using IZK to prove okay the KDF is computed correctly, and the prover no KP and secret M that generates C1 C2. And that's the whole framework. And also we do some performance to compare with DACO. So with different network with different payload size. So yeah, you can see the number is like 10 times faster than DACO. And also we conduct a global scale experiment. So let me explain a bit. So here the purple nodes is the verifier, and these yellow nodes are provers in different countries and areas. So the yellow part, the number of the yellow part means that the time that when the server is hosted by the Coinbase, we are like to query the balance of BTC or something like that. And the green part, it means that the server is hosted by Twitter. We are like to query the number of followers. So also we separate the whole protocol into online and offline. So which the reason that we want to do this is that we can do a lot of things before the prover establish the TLS session. And we want to finish the whole 3PC handshake before the server timeout. So it's very important that we reduce the time of online. So in this case, in our experiment, we show that even in the worst case, we only need like 10 seconds to complete the whole 3PC handshake. And usually the timeout time, I think, is about 15 seconds. So yes, we also can like to move the verify to close to the approver to make sure that to make the time much smaller. So yes, this number show that our protocol is kind of very scale, and we also like integrate to our product, and which means which shows that it's kind of it works very well. Yeah, so basically, we put our paper on ePrint, and it actually it's got accepted by Usenix security this year. And yeah, I'm very happy if you have any questions to discuss with me online or offline. Yeah, that's basically all the presentation. Thank you.
Thanks a lot for the talk. It was really interesting. You have really good results. It's impressive. I don't see any questions, unfortunately, on the chat. And on my side, I need to read a bit more about Ole to be able to ask you questions. So I'm sure I will send you a few offline.
Yeah, sure. Yeah. I'm happy to hear any questions offline. Yeah.
Thanks a lot again for the talk, and have a good day, everyone.
Yeah. Thank you. Thank you, Amber.